Okay, welcome to the sixth day, the last day of the program, ATAL ATP, that is the FDP program. Today is a very important person, Dr. Sankar from Academia Sinica. He is well known for us, Dr. Sankar. He started journey from the Madurai Thyagaraja College. Then after that, this joined with the Crystal Growth Center, Anna University in the year of we have joined almost in the year of 2003 in the Crystal Growth Center, Anna University. After completed his PhD, then he moved to Taiwan for a postdoc research fellowship in the year of 2009. Then slowly he's moved to the higher position. He have published a lot of major publications in the regarding crystal growth materials and devices. Then after move to the Dr. Sankar is the research scientist. Now currently is working the research scientist. He have lot of facilities regarding semiconductor material and devices and crystal growth techniques also. He have expertise. During in the PhD itself, he have done lot of crystal growth, nonlinear optical crystals he have done and characterization techniques. Now we move to the slowly the semiconductor material and devices towards the computing facility, quantum material and devices. Let us welcome Dr. Sankar deliver his lectures.
Thank you very much, Tangavel. Thank you for introduction.
And happy to say that Dr. Shankar visited almost many countries from Taiwan, like Switzerland.
Okay, thank you,
that is
Tangavel.
also very good. We are happy that you are one of a colleague for us. During the same period, we worked together, and thank you for that.
Thank you. Today, I'm going to talk about the new quantum material development and also some of the crystal growth technique, how we are using for a different material, and then follow up, I'm going to discuss some thermoelectric material. Good afternoon, everyone. My name is Raman Shankar. I'm working as an Institute of Physics, Academia Sinica, Taiwan. I'm an associate research scientist. Our lab mostly funded by government agency. In our lab, including Academia Sinica, funded for all the instrument and postdoc research fellow, including PhD fellowship. Currently, my core facility funded by TCCM. Every year, I need at least 25 million Taiwan dollar to run my lab. Okay, this is the Taiwan. I'm the top of the Taipei. Then in the Taipei, we have a city for Nangkong. The Nangkong Academia Sinica is surrounded by some mountain. This the left side is showing total Academia Sinica Institute. Then the right side one, the Institute of Physics. The front portion is an old building. The back side mostly a new building. All the crystal growth lab in the second floor. Okay, this is our entrance of Institute of Physics. First, I introduce what we are doing in the Institute of Physics, because we have a three kind of physics institute, like quantum physics and biophysics and high energy physics. Just I show you 5 minutes video. People need to understand what we are doing. Okay.
The Institute of Physics of the Academia Sinica was founded in Shanghai in 1928 and re-established in Nanyang, Taipei in 1962. The Institute's primary mission is to promote basic physics research. Its three major research directions are medium and high energy physics, physics for active and biological systems, physics of quantum materials. The fields of study include particle physics and cosmology, atomic and nuclear physics, condensed matter, materials and surface physics, biophysics, fluid mechanics, and nonlinear physics. The Institute has over 40 research scientists, supported by about 400 research and administrative assistants, graduate students, and doctoral scientists. It's committed to pursuing excellence in research and providing high-quality education and training to future scientists. In the area of medium and high-energy physics, the Taiwan Neutrino Experiment is an international collaborative project conducted at Taiwan's second nuclear power plant. It pursues studies of neutrino magnetic moments, electroweak and coherent interactions, as well as a new detection window to search for low-mass dark matter. The Institute of Physics is also participating in many other international research projects, including the AMS experiment on the International Space Station. This experiment seeks for signals of antimatter and dark matter in space, hopes to unravel the secrets of the Big Bang, and possibly new structures. The Institute of Physics, together with other Taiwan institutes, have provided key hardware and software technologies and has established the AMS Payload Operation and Control Center in Taiwan. In the ATLAS experiment at CERN's Large Hadron Collider successfully discovered the Higgs particle. This breakthrough proved that the standard model of particle physics is still valid. The Institute is the first Tier 1 center in Asia and is processing the vast amount of data collected from the ATLAS experiment. In the area of physics for active and biological systems physics research, an interdisciplinary approach combines biological and phenomenological physical models to understand physical mechanisms across the scales of cells, tissues, and organs. Cells are subjected to mechanical influences in their growth microenvironments. To understand the effect of dimensionality on cells, we used microfluidic channel technology to blow bubbles of uniform size that produce uniform porous scaffolds. The scaffolds could control the cellular growth in a three-dimensional microenvironment. This technology, already licensed to industry, has tremendous potential in tissue engineering and drug screening applications. Nanometer nanoscale molecular dams are nanometer pinch points formed by nanofabrication, capable of focusing strong electric fields and field gradients. Molecular dams quickly gather trace protein molecules and increase protein concentrations more than 100,000 times within 20 seconds. This will facilitate development of screening chips for cancer and other diseases. The high penetrating power and 3D nanometer resolution of our synchrotron radiation X-ray microscopy unravel the physical mechanism of fireflies' luminescence. Interdisciplinary researchers are combining molecular physics, molecular structures, and pathologic physiology to investigate molecular and cellular behavior from the macroscopic dimensions of organs to micron and nanometer fluid systems. This multi-scale effort seeks to understand how cells maintain efficiency and the basic mechanisms of organ formation, and hopes to ultimately shed light on the emergence and metastasis of cancer cells. Research on the physics of quantum materials mainly includes the growth and characterization of novel quantum materials, fabrication and imaging of nanostructures and interfaces, study of low-temperature physics and superconductivity, spin electronics, and magnetic nanostructure and transport. Recent research results include, as quantum materials represent an important direction in searching for and designing future emergent materials, researchers have been studying the growth and characteristics of quantum materials. Observation and understanding of the distribution of vacancies in iron-based high-temperature superconductors have illuminated the correlation between their degree of orderedness and superconductivity. Working with ferromagnetic topological insulators, researchers for the first time verified that the quantum anomalous Hall effect can be extended to macroscopic and three-dimensional systems. Researchers combine both electron transmission and scanning tunneling microscopy techniques to directly observe nanoscale capillary phenomena and discovered that the ratio of the size of silver nanodroplet to the diameter of carbon nanotube was a critical parameter. Research on a hydrophobic solid water interface discovered that hydrophobic surface can effectively capture gas molecules dissolved in water, and that the gas molecules may form several types of nanometer structures in condensed phases at the interface. To promote forward-looking physics research, the Institute of Physics is constantly acquiring and maintaining advanced equipment and instruments, such as its core facility for nanometer processing, helium liquefaction facility, and precision machine shop. To cultivate future.
Thank you for watching. And this is our lab member. Without them, I cannot produce any high quality impact paper. Mostly in my lab, all Indian students, only one secretary from Taiwan is. In Taiwan, we offer a lot of PhD as well as master program for government announcing a lot of PhD scholarship. Here, the left side one, all are tuition fees waiver one. But in this case of THB Nano program, every year we provide first and 2 years $40,000 NT. And if you qualified the first year, then we pay almost Indian money, 1.5 lakhs Indian money. If any one of your students interest, please ask them to apply for this kind of program, because I'm in the panel for this kind of program. I will really support our Indian people. Let's start my research. Most of in our lab, we interest on topology insulator, Dirac semi-metal, Wiley semi-metal, and thermoelectric. Recently, we started 2D material also. In our lab, we have a different kind of work is there also. We mostly focus on geometrical frustrator magnetic material. Everyone know the structure very important for magnetic material. For example, we can classify it in a different type. One is spin dimer. Spin dimer nothing but the nearest neighbor one, J1. Anywhere you can connected all the atom, it's like a dimer one to one coordination. Second one, triangular lattice. Third one, square lattice. Kochhammer spin geometry, and honeycomb lattice spin chain. Among these five, we can consider the Kochhammer is the more frustration than other magnetic material like a handle gap, spin liquid, spin spiral. This kind of material also we are working. Pardon? Because we are mostly for growing single crystal. Either we grow for new material, we discuss with the theoretical people. After that, we characterize like a magnetism, thermoelectric, optical, and surface studies like STM, STEM, everything. In my lab, mostly we working for a correlated quantum material. The aim of our lab, once we produce a new material, we transfer for advanced characterization and also device fabrication. How to implement for this kind of material for technological transfer. Then another thing, if you are talking about the correlated quantum material main, these all are material very important, like insulating 2D magnet. One of the example is chromium iodide. Alternate 2D magnet is iron germanium telluride, Kochhammer metal, quantum critical point, quantum spin liquids. Quantum spin liquid nothing but you have a magnetic structure. If you go to low temperature up to millikelvin, you don't have any transition up to go to the millikelvin. If we, this kind of material, if you dope either electron doping or gold hole doping, definitely that material possible for superconducting material. And also recently people working for magnetic topological material is very, very important. The first material is the manganese bismuth tellurium. I have a more than 150 international collaborator, and in the national collaborator almost 92 people. You people know that Taiwan very small country, that's why we have a less collaborator. This is my research direction because recently our lab mostly focus on topological material, topological insulator, semi-metal and semiconductor, and layer material like a transition metal diglycinide and mesfit superconductor. Recently people working for superconductor like a non-centrosymmetric superconductor and topological nodal line semi-metal. This thing I will talk to you later, coming slide. These are the material. You can clearly see the non-linear material mostly I grown in our crystal growth center. This is my initial seed for my career, everything. Then some of the important highlight of our crystal growth, our lab, we publish a lot of papers. I'll just show you 1 or 2% paper here, because we are the first group grow the tantalum arsenic, lead tint selenide, and sodium bismuth. All are be published in Science, Nature Physics, Nature Material, and including chemistry of material. One of the thing I need to inform you, the bismuth, the diselenide, we are the first group grow exactly stoichiometric of bismuth triselenide, because most of the group they grow, but they have a mostly selenium vacancy. Because if you have a selenium vacancy, you cannot exactly point out the topological nodal line band gap. And also, we are the first group demonstrate the indium selenide single crystal. In this crystal, I think Rajesh also worked together with me. We almost published more than 50 nanoletter only for this sample. Then some of the grown single crystal, I will show you coming slides. These all are grown from our lab, all are very high quality single crystal. Then some of them 2D material, we grow from the Bridgman or CVT, including topsider crystal growth also. These all are grown by Bridgman method. I will introduce my lab. What are the facilities available in my lab? Because some people, if you need to collaboration or you need to utilize my lab, always welcome. Just send an email to me. Then you can come for intensive or you can visit our lab also. This is our material in this lab. We have two kind of glow box. One is nitrogen atmosphere and argon atmosphere. This other one, this is a solution growth lab. this is my career started. That's why I created one separate solution growth for my entertainment. I can do whatever I want. That's why I created one separate solution growth lab also. Then this is a CVT, zircon crystal growth lab. Another one, metal characterization lab. Here we have a Bridgman, arc melting, and also some different atmosphere we can grow also. This is a top-sided solution growth, Bridgman. High pressure, we can go up to 8 GPa. We can grow some of the metastable material. That material sometimes is unstable. Only we can grow in a high pressure only. And also we have a Janan lamp floating zone also. We can grow any kind of concurrent melting more than 3,500 or 4,000 material. We can, using this floating zone furnace, we can grow all kind of oxide material, including metallic or alloy based material also. Then we have a metal characterization separate lab like X-ray, TJDTA. TJDTA we can go up to 1,500, including DSC. We have a different kind of microscope. Auto lab we can measure for a sensor, catalysis purpose, and also we can use for you can use supercapacitor also, including we have a battery setup, IV measurement. This all done by Rajesh only. He only arranged everything in my lab. And also we have a VSM and PPMS. PPMS we can go up to 0 Tesla to 9 Tesla. The temperature range 2 Kelvin to 400 Kelvin. But in this case of VSM, we can go from 0 Tesla to 7 Tesla. The temperature range, first range 2 Kelvin to 400 Kelvin. After that, we can change a module to 300 K to 1000 K up to we can measure the magnetic measurement. And also we have a high quality Lave XRD also in our lab. And also we have a thermoelectric calibration like a GEM3 laser flash measurement, including hot press. These all all are instrument available in our lab. Okay. Then another thing, recently we make one integrated core facility characterization as well as growth measurement. In this core facility, we never explore our sample in the atmosphere. Everything under high vacuum only. Okay, I'll show you. This is the system we have. Like we have a metal MBE connected with UV chamber with ORPS and PLD, SPM also. Okay, I will go one by one. If anybody interest, you need to do for ORPS or metal MBE. Just you can clearly see, go to this website, just to go to the application form, fill up and send to me. Then I can arrange a slot for you. Every year, I think you can utilize for 3 times. This is the MB system. You can, this is MB chamber. We have read everything along with the MB. We can go up to 10 power minus 10 torr. Mostly we use manganese, selenium, tellurium, bismuth, Fe or the target material. This kind of material, if you want to grow, you can send your student. They can spend. We can ready to teach them. Here the temperature range we can go to minus 150 to 1200 Ca also. And also we have a various temperature scanning probe microscope attached with the AFM also. This is the ORPS measurement. It's a very rare measurement. You can do all the topological insulator, Wiley semi-metal, or including Northern superconductor. You can clearly see the band gap of the material. And also surface phenomena. What is the phenomena is going on? We can clearly see that one also. Here we use for 6-axis manipulator with a 2-stage. Each stage have a different temperature region. You can you can characterize your sample. Here we use almost 10 power minus 11 torr for the ultra high vacuum also. This is a transfer system. You can clearly see there's a center one. This is everything connected with all the instrument, including ORPS, STM. Once you grow the film, directly you can go and characterize all the sample. Within a week, you can write a very good paper. Let's start the crystal growth. Okay, the crystal growth is a very high demanded profession. Okay, once if people know crystal growth, because still many world looking for a high quality single crystal. I really proudly say I coming from Crystal Growth Center because I learned everything from the Crystal Growth Center. I really thank my advisor, Professor Jayavil, because he allowed me to do all kind of crystal growth technique. When I did my PhD, I started theoretical with Professor C.S. Subramanian, but I slowly started a solution growth, and also I moved to high temperature flux growth, including Bridgman, everything. But crystal is very important. Once you want to grow any single crystal, you must think carefully what is the method very useful for in this crystal. Another thing, the size and morphology, including we can doping effect as well as impurity also play a vital role for every physical characterization. And also the growth choice of the growth method also important, very important, and stability. For a neutron, if you want to do the neutron magnetic measurement, at least your sample need 5 to 10 gram large size sample. That means you need to decide what kind of method we want to grow our material. Okay. Then what is single crystal? Everybody know, but I simply say the arrangement of atom in a three-dimensional way in a regular manner. Why we need a single crystal? Because single crystal only is a meaningful measurement, everything, because we can do anisotropic property other than cubic, because you people know all the direction for cubic is same. But if you want to do all the characterization, some of the orientation, it definitely give higher property than other one. What is the use of single crystal? If we say, you can see Taiwan is the main producing semiconductor industry. Okay, we can grow the silicon chips, yttrium aluminum garnet for a solid state laser, beta beryllium borate for doubling the triple the frequency, lithium niobate, quartz crystal. These all are very useful for industry application. Before you are going to start the single crystal growth, at least you need to understand the periodic table, because without periodic table, you don't know the material property. At least you need to understand the MST data. You cannot go and directly touch all the chemical, because some of the chemical really poison chemical in the periodic table. If you want to handle for an S block element like a potassium or barium, you need an argon atmosphere glove box. In this kind of transition metal, these all are magnetic one, because some of them here poison metal like a mercury, cadmium, all are poison material. Some of the air sensitive also you need to careful to handle. But if you come to B block element, thallium, lead, bismuth, tin, and including fluorine, all are poison material. That's why if you want to start a crystal growth, at least you need a fundamental knowledge of periodic table. Okay. Why we need a single crystal? If we want to order for any single crystal for 2 mm by 2 mm for a US company, they are selling almost 590 US dollar. You can clearly see the size of the crystal very limited, because nowadays India, you people not get that much research funding. That's why if you have a in our institute, some of the people grow single crystal mean really good for your future research purpose. You can clearly see all the sample more than 500 USD. Then if you converted our Indian money, it's very expensive. Okay, we can go for a different kind of crystal growth technique. Today, we can classify it in a different crystal growth method for a four. One is melt, solid, vapor, and solution growth. Melt growth still we can classify it into two types. One is by with crucible, another one without crucible. With crucible, either you can use platinum, quartz tube, or corundum kind of crucible. That kind of undercome for Bridgman, Zigorski. Without crucible, we can use for zone movement, Bernoulli method, floating zone method. Solution growth, we can classify it into two types. One is a low temperature, high temperature. We can classify slow cooling or evaporation method. For high temperature, we use mostly for a flux growth method. But the melt growth, mostly for a directional solidification for melt, if we're per hour. For solution growth, supersaturation very important, per day. Vapor growth is a micrometer per hour. Okay, this is the growth method we can grow. Everything depends upon the nucleation rate. Nucleation rate nothing but number of nucleation form per unit time or per unit volume. This is very important for all the crystal growth technique. Okay, let's start the solution growth, because why I started solution growth mean some of the people think, oh, if we grow the solution growth, we cannot publish a high impact paper. Not like that. Later I explain how we publish using solution growth method sample. We almost publish more than 23 impact paper. Okay, here the crystallization take a three part. One is achievement of supersaturation or supercooling, the formation of crystal nuclei, and growing large size single crystal. Here, supersaturation is an important point. We can define by del C is equal to C minus C star. C is nothing but actual concentration of the solution given by the temperature, or C star is the equilibrium concentration at given by. In the supersaturation, we can classify three type. One is equal to 1 mean the saturation, greater than 1 mean supersaturation, less than 1 mean under saturation. Because in the solution growth, another parameter very important, nucleation kinetics. Nucleation is the important phenomenon for crystal growth technique. Okay, we can classify it in a two type. One is a primary nucleation, secondary nucleation. The primary nucleation we can classify it into two type. One is homogenization, heterogeneization. Homogenization nucleation, nothing but spontaneous nucleation. But in this case of heterogeneous nucleation, you can induce by any foreign particle, or either wall of the container or impurity or seed crystal. This kind of thing you can induce by growing large size single crystals. For a solution growth, everybody must be understand the Mayer solubility diagram. This is nothing but concentration versus temperature. Here we have two different kind of solubilities there. One is a positive temperature coefficient, another one negative temperature coefficient. The positive temperature coefficient, nothing but if we increase the temperature, the solid concentration also increase. One of the best example, methyl ammonium lead iodide. But in this case of negative temperature coefficient, if we increase the temperature, solid concentration is decreased. One of the very good example, methyl ammonium lead bromide. If we go and check in the literature, you can clearly, and also select of the solvent, very important. What kind of material you are growing, that is also very important. Another thing, we have a three kind of solution growth method. One is slow cooling, evaporation, and also temperature gradient method also. Then in this case of solvents choosing, you need to choose high solid solubility, high positive temperature coefficient, low viscosity, and small vapor pressure, and less corrosion and non-toxic. Don't use any toxic solvent. Then you can use for mostly for a few mood or inside the glow box. Okay. And okay, what is the advantage? Some of the high temperature materials sometimes is a become decomposed. That kind of material we can grow mostly for organic material. We can choose for the solution growth method. Some of the material undergo phase transition. There is a three kind of polymer option. You can clearly see 6-cyano HPBI. They material have a three kind of polybronzim is there. Each polybronzim state you can define by the temperature. This one is below room temperature, one is the mid temperature like a 50 degree, another one 100 degree. This kind of different temperature, same material you want, you choose for only for a solution growth method. In this method, really instrument very inexpensive, and also we can grow this kind of single crystal. We have only for less impaction crystal structure as well as the stress also. But it's take long time. It's take almost more than 1.5 months. If you have any disturbance in between your growth, definitely total growth is contaminated. Sometimes we have a solvent inclusion inside the material. Sometimes we have a solvent inclusion or the nylon thread give the some of the stress inside the material. This is evaporation method is all grown by myself in a crystal growth center. You need perfect seed crystal, then inside the solution. Here temperature is constant. You no need to reduce it. Once you evaporate all the solvent, your size also, single crystal also increase what size you needed. Okay. But in this case of slow cooling technique, you need to reduce the temperature with respect to how your solubility. Okay, maximum 0.5 per day we can grow all kind of single crystal. The right side one, the KTP crystal, people grow using solution growth method also. Because why I choose before for a solution growth, recently people working for 2D perovskite mostly grown by solution growth technique only. because here the reduction proper perovskite is a 2D material. We can grow 3D material also, but the 2D material is a key feature is high conductive, large surface area. We can choose the functional group and what are the chemical composition also we can use for the this kind of material. Because you people everyone know perovskite structure is ABX3. Here A is cation, B is a metal ion, and C is chalide. Because here we are going to make it hybrid perovskite, like inorganic material as well as organic material combined together to form a layer material for a 2D perovskite. In this case, we have a two choice of growth. One is RP phase, that is another one TJ phase. RP phase, always you have a van der Waals gap. It's similar like a 2D material. But the DJ phase, you have a, there is no van der Waals gap, but in between you have an organic spacer. There is a metal ion, in between you have an organic spacer to form a layer material. What is the use of this kind of material? For a chemical property, you can induce a defect, surface modulation, and also you change the van der Waals gap, including you put some intercalation, and also you can do the functionality. Okay, but the application side for physical property, you have high electrical conductivity. You can tunable the band gap with respect to change the structure, layer structure, and spin polarization and strong electron correlation effect in the 2D perovskite material. But in this method, you can always you have a direct band gap material, strong absorption coefficient, longer carrier coefficient, and high mobility. The right side 3D perovskite, just example for methyl ammonium lead bromide is one of the best 3D perovskite material. But in this 3D, we can convert it into 2D material also, including or bulk organic cation. Like the formula, the right side, left side, I can given A dash AMX3. These all are maybe later Rajesh explain clearly everything. Here, A dash is a butyl ammonium organic spacer. Another one, A dash is a small organic methyl ammonium based. The metal ion mostly for lead or tin, and X is a chlorine, bromine, iodine. Okay. Here, interestingly, we use iodic acid as a solvent. Everyone know, and also you need to convert 100% iodic acid. If we heat at 130°, we have a loss of sometime iodine. That's why we add some phosphoric acid to stabilize the iodine nature also. Here we cannot use it because we are using chlorine, bromine, iodine, right? We cannot use for directly for lead iodide or lead chloride. We use mostly lead oxide to dissolve under the 130°, and we use for methyl ammonium reacted with HI. In this reaction, always you can keep it for 0° because any acid react with amine group, it produces lot of heat. That heat sometime decompose the organic compound. That's why we always use for 0° reaction. Okay. And also in this method, we can tune n equal to n mean number of layer. You can tune with respect to number of layer. What is the motivation? I think these all are motivation discussed by Rajesh. Just I can this the 2D perovskite we can create natural quantum well, high quantum efficiency, tunability of band gap, and the stability is the question mark for a 2D material. That's why Rajesh did excellent work. He published for solution growth high impact paper. I later discuss that one. These all are some of the 2D perovskite we reported in grown from our lab. I can show you. This is a unique material because one of my colleagues, CM Raghavan, everyone know. That time we started for reduction proper material. That time we need to really prepare this kind of 2D material perovskite. I think that time Raghavan work in Korea because this kind of solution growth, we need an expert. That's why we call for a postdoc. After he came, he published very nice nano letter paper, and then he moved to UK for Marie Curie fellowship. He grow in this method. We both try this one. We grow n equal to 1, n equal to 2, n equal to 3, n equal to 1, 2, 3 being number of organic layer inside the 3D material. In this method, because if you add for methyl ammonium chloride or anything, you need to add by drop wise. If you add suddenly, then it form both N1, 2, 3 in combined, we cannot grow high pure material. Another thing, how you can claim this is a N equal to 1, N equal to 2 layer or 3 layer. You can clearly from the XRD, you can see the 2 theta, the 10 theta below only one figure appear mean it belongs to N equal to 1. Then second figure, you can clearly see the 10 below, we have a 2 peak, that it means N equal to 2. Third one, you can clearly see the N almost 3 figure. The main utilized for this, changing the number of the layer, you can tune the band gap of the material. You can clearly see the PL1, the right side, N equal to 1, N equal to 2, N equal to 3. You can tune from the wavelength from the 500 to 650 and also band gap. And also we did lasing studies also is really stable up to room temperature. Another thing, there is a big problem, methyl ammonium N equal to 2, because most of the people grown that one. The problem here we face the stability of the material. You can clearly see the bottom of the butyl ammonium methyl lead iodide. You can clearly see the PL measurement. The 0 minutes, the PL signal is stable. Then 30 is quench off of the thing, and 1 hour completely make it 0. But that time Rajesh and me, we work together. We need to challenge the work, how to make a stable perovskite material. Rajesh did for changing the organic space and like a formonium amide. Then he used that formonium amide to prepare this sample. The top A figure clearly show the PL nature of the PL. Up to 1 hour, there is no decomposition in the surface of the crystal. And also he did a photo detector, everything. You can see the stability of the right side, both the material comparison. The stability up to 7 minutes is very stable. After he grow, we write very high impact paper like advanced functional material. We mostly emphasize the stability of this a single crystal, that also we grown from the solution growth. We publish almost 23 impact paper. Not only this one, Rajesh did a DJ method also. This is a very difficult to grow this kind of single crystal because it's a long chain organic material. Rajesh tried this one, and also we prepare this a DJ space. People claim that it's very difficult to grow this kind of material, but Rajesh did. He showed all the FET and photo detector, including all the device performance. Later he discussed his slide. He published another advanced material. He got the best paper award. After that, he got the IIT rookie for assistant professor also. Then I can move on vapor growth. Okay, another technique. If you have any other doubt in this previous section, maybe Rajesh explained clearly. Vapor growth also important technique, very important technique. You can purify your material as well as we can grow some of the material we cannot melt like MOS2, WS2. The material have a high melting point. Everyone know we have a maximum CVT temperature is 1200, because if you go above the 1200, we cannot use for a quad strip as a growth technique. And also in our lab, the right hand side, all the material we have available, 2D material, 2D transition dichocolate material, including monochocolate material also. Here we mostly use for chlorine, iodine, bromine, including hydrochloric acid transport agent. The transport agent is a deciding authority to how to move from the source end to growth end. And also you need a temperature gradient, at least 50 degree to 100 degree 2 zone, or if you are using 3 zone, what are the furnace you are using. Temperature gradient very important for this kind of the growth material. This we have a 2 zone, 3 zone, more than 10 to 15 furnace available in our lab. These all are single crystal grown from the chemical vapor transport. Then some of the material growth temperature or the optimized temperature we kept here. The problem, you need to understand how much volume you are taking according to, simple formula PV equal to NRT. According to, you need to use the transport material. If you use excess transport, it's possible to explore because everything is a closed system. Once you vacuum and resealing, then if you inside the iodine or chlorine anything, once you heat, the molecule also increase. That's why you need to calculate everything with respect to temperature. These all are 2D material and optimized temperature growth also. Why I show you specifically CVD technique? Because we recently grow some of the topological nodal line superconductor. Lead tantalum diselenide is a non-centrosymmetric topological nodal line superconductor. In this physics community, people very difficult to grow this single crystal. One of the main single crystal pioneer is R.J. Kawa. He make the powder, but he claimed we cannot grow the crystal. Because I tried this crystal because it's really first topological nodal line superconducting material. The temperature range 3.8 Kelvin. Here two problems at that time we face. One is we have a two-phase group, same material have a two-phase group. We need a non-centrosymmetric material. Another thing, if we use kind of a normal transport like a chlorine, iodine, and bromine, we cannot grow the crystal because always to form tantalum diselenide. But I try more than 1 or 2 months, then suddenly click, oh, why don't you choose for lead chloride as a transport? Because self transport very, very important. I use, then finally I got the very nice single crystal. That is the first single crystal showing topological nodal line superconductor. You can clearly see that TM is exactly because here tantalum occupancy is a 0.5, because the reviewer asked how you claim this is a non-centrosymmetric. And also we did an excellent STM. We find out the superconducting gap also. It belongs to S-type superconductivity, PCS3. The same method I try thallium because you people know 3.8 Kelvin good for STM ORPUS is take a long time, more than this a 6-month work. And also I already informed to you people why single crystal very important. You can clearly see the right side, the MH data, magnetic measurement data. The parallel perpendicular showing superconducting fraction totally almost 3 order higher than the normal one. You can clearly the red and black. The black is a parallel one. The red one is a perpendicular one. See how much difference is the superconducting fraction nature. The same family I tried with the thallium one. You people know thallium how it very poison one. But thallium is a centrosymmetric topological nodal one. We grow this one because in this case, we prepare this one almost 7.2 K superconductivity. Almost we double the superconductivity one. And also we publish with a science advance, including nature physics in this material. Another topological nodal line material, sodium aluminum silicate. People never heard about, because mostly we heard about silicon have a 4+ valency, right? But in this case, silicon have a 4- valency. The silicon and aluminum and silicon coordinate to form a layer. In between the layer, we have a sodium content. The sodium content going to decide what is your superconductivity transition temperature, because you can tune that superconductivity transition with respect to sodium content. Another thing, we cannot use this sample. Once you grow, if you take it out, within a second is a decompose. That's why every measurement, you break all the tube, everything. We can go with a glow box and you measure, including ORPUS, STM, you need to proper carrying. Then right side, you can clearly see the 7.2 K superconductivity magnetic data as well as superconducting MH data also. Another 2D material we called as misfit layer compound superconductor. Okay, because most of the thin film people always talk about heterostructure kind of thing, because once you can grow the thin film, you can deposit another film, the top of the another film also. We people called as a heterostructure. One day I decide, oh, why not we can grow for a single crystal using like a two material together to form a like a heterostructure. I choose, that's why we called as a misfit material. I choose one is monochocolate, another one 2D material like a trichocolate, right? One is a hexagonal structure, another completely cubic structure. We put together to make a misfit compound. that is called as in common state kind of material. You can clearly see we can choose this kind of misfit compound. What are the layer like before I talk about, right? A number of M, number of the N, you can choose according to you choose the 2D as well as monochocolate, change the structure and make it like a new material like a thin film. See, I use for a tin sulfide entirely semiconductor material. TAS2 also completely semiconductor material. We put together to form a misfit compound. I use almost 900K, 900C and as well as 800C for a growth temperature. In this method, we use for iodine as a transport. The synthesis temperature already I mentioned. Then you can clearly ask me how you are claiming, sir, this is belongs to heterostructure kind of thing. You can clearly see the X-ray one, the black one, you have a 15, 30 and 45. There is a periodic XRD. Once if you put the tin sulfate TAS, you have a super periodic to be in between the red color is coming, okay? And also clearly see the TM. The white one showing the tin sulfate, the black one you have inside there is a two layer. That is a tantalum diselenide. It form the hexagonal structure the top of one. Inside is a you have an orthorhombic structure. And also we confirm with this one anisotropic of this material. It's showing 3.1K superconductivity. And also you can clearly see that resistance of this both direction is totally different. And also we apply different pressure for this material. We enhance up to we use 1.96 GPa from the squid. We can enhance from the 3K to almost 3.9K TC value also. And also upper critical point in the in plane 6.64 Tesla, the cross plane 0.22. That's why I say single crystal very important to measure the physical property. And also we check the MH and MT data clearly showing 3.2K. And also we check with the specific heat measurement. And also we calculate the Sommerfeld phononic coefficient, everything. It become a weak coupled PCS superconductivity. This is all our we grow different kind of misfit compound using chemical vapor transport and also showing the superconductivity transition also. Maybe Tangavil is okay or I can continue. I think your mic is.
No, just go ahead. Go ahead.
Okay. And also we did for the defect physics because most of the people say, oh, my material defect is there, mean what can I do? Sometimes defects also give excellent property for the measurement. I can go through one by one, then I can explain to you. Then in this case, previously we talked about the topological superconductor, right? Here I'm talking about topological nodal lines and ferromagnetic. This is also 2D material, but is packed with like a 3D one. Okay. In this method, if you prepare using CVT method, we cannot grow 1:1 exactly gadolinium antimony tellurate. We have always different composition for tellurium and antimony because in the periodic table you can clearly see antimony and tellurium almost very near the compound. You can disorder this almost to grow the disorder compound. The left side you can see if you produce the defect or if you grow non-stoichiometric compound, either tellurium rich or antimony poor, you have a three kind of space group up here. One is orthorhombic, then center one is a clear orthorhombic one, and trigonal one. Trigonal one clearly showing the topological nodal line. You can clearly the top one showing the RF spectra. The arrow clearly indicate the nodal line. That down one is clearly showing the surface brilliant zone surface phenomena. You can clearly see that antiferromagnetic around 16K is a clear indication of this crystal belongs to antiferromagnetic nature. We almost publish in this material in a science. Another one, two-dimensional transition metal phosphorus. This also we grown from the chemical vapor transport. We in this metal phosphorus is recently all the physics community very interesting because it's optical material as well as semiconductor material as well as magnetic material. That's why it's very important for recent day. We can grow this kind of material in two different ways. One is MPS3, general formula M2B2S6. In this case, two structure is available. One is hexagonal, another one monoclinic. But the B structure, M belongs to 2 plus. That means you have a 2 transition metal, magnetic material available. But in this case of C structure, you have a monovalent like a copper or silver, but the metal have a 3 plus like a chromium, iron, cobalt. This kind of metal come for this two structure. But in this structure B belongs to, we can grow both hexagonal, monoclinic, but in this case of C only appear in a monoclinic crystal. I can explain in this kind of magnetic.
Hello? Kindly mute. Hello?
Okay, this kind of material have a different magnetic structure. I already informed you antiferromagnetic, but still we can classify antiferromagnetic in a 3 type. You can clearly see the first one belongs to ferromagnetic. Ferromagnetic means all the magnetic people know all the spin align in a parallel way, almost similar. But in the antiferromagnetic spin, one is up, one is down, but we can change the up and down spin in a 3 different formats. One is zigzag. You can see the first plane, all spin showing the down one, the second plane showing the red color one, up one. This kind of pattern we called as zigzag antiferromagnetic. Stripy, the same plane you have up and down spin. The needle one plane down, one plane up, then systematically come. This kind of antiferromagnetic, we have a different magnetic structure also. The right hand side, we can clearly show the magnetic measurement with respect to temperature, clearly show all the transition temperature with respect to different material also. All belongs to 2D metal phosphorus trichoepithelium, right? But in this case, this material have a van der Waals gap also. We can claim the spin model for a 3 kind of one. One is Ising, XY, hence per Hamiltonian one. And also each metal have a spin also there. FePS3 realize spin equal to 2, it belong to Ising antiferromagnetic. Almost the transition temperature is 123 Kelvin. MnPS3 is spin equal to 5 by 2. The spin with respect to unpaired electron, we can claim this S equal to 1, S equal to 5 by 2, and S equal to 1. This belongs to unpaired electron magnetic material. Then NiPS3 belong to N is S equal to 1 is the XYZ type antiferromagnetic. Here, all the magnetic material aligned by honeycomb lattice. You can see all the material honeycomb lattice, because in this honeycomb lattice, J1, that is a nearest neighbor atom, second neighbor is also J2, third one J3. Already I informed you, if you create a defect in this is a material, that you can clearly see the green one is a sulfur. Here J3 via super exchange through sulfur. If you create the sulfur defect, this material showing sometimes a strong ferromagnetic nature also. These all are grown for CVT method. Then NiPS3 belongs to D8 electronic configuration, is octahedral coordination. Then B2X is a below honeycomb lattice. You can see the honeycomb lattice, and below honeycomb lattice is coordinate with the phosphorus sulfur one. In between, you have a van der Waals force. The van der Waals force very important. In this case, we need to check either we have any phase transition is occur if we apply the fresh pressure. But we grow the monolayer, we never see any phase transition occur in this monolayer film. But in this case of bulk material, because you have a van der Waals gap, we apply up to 30 GPa, we clearly understand is move to C2M to C2 bar M and P3 bar 1 mm after the first transition to second transition. You can clearly see the X-ray diffraction using high pressure X-ray we did. Up to 10 GPa, we never see. The first order transition occur only above 10 GPa. After that, 24, we clearly see it transfer to monoclinic to triangular phase transition. But in this case of A direction, B direction, there is nothing change. Only we have a change in along the C plane and also beta value also. You can clearly see the lattice parameter completely different than the pure one. And also we dope with the magnetic material along this nickel and iron phosphate. We change the transition and also change the in plane and out of plane antiferromagnetic transition also. In this slide, you can clearly see initially is a broad maxima. After that, we dope small amount of iron in the nickel side. You can clearly see from the 1D to 2D magnetic transition, the broad maxima clearly has appear, and also you can clearly see the sharp transition. With respect to the composition, you can reduce the TC value from 162 up to 180. Then I already discussed about the sulfur vacancy. Once we create a sulfur vacancy, that material provide ferromagnetic nature at a low temperature, and also we dope the cobalt inside the iron side. We create a high spin nature. That high spin nature we did for OER and HER catalysis. This is very, very important. In this material, once we dope the cobalt to enhance the high spin active center, to enhance from 1.6 to 1.4 voltage, that is the excellent oxygen evaluation reaction material. And also we check with XCAS as well as XMD also clearly indicate that the magnetism coming from the ferroelectric nature, and also we published from the advanced material in this material. And recently I already informed, right, NiPbS3 belongs to antiferromagnetic out of plane, is clearly shown from the left hand side, and antiferromagnetic nearly in plane for NiPbS3. We dope, we check with the terahertz manganon using optical high magnetic field optical measurement, and recently this material is accepted for nature material. And also the defect for sulfur creating a local spin chain direction. You can clearly see the spin totally, the first figure showing the spin direction totally different opposite direction. We found that one. Then we create including PL and second harmonic generation, everything. Then we are the first group demonstrate the defect producing different local spin. Then we publish advanced material. Almost this is the 331 impact paper. Then maybe I can stop here. I need to acknowledge some of the important people in my career. Just I like to thank, maybe because Rajesh need to talk some of the things. Oh.
Yeah, it's okay, no problem.
Sorry.
It's fine, no problem.
I need to acknowledge for my professor, and Professor Fang Changcho is my postdoc boss, all my director. Nearly without them, I cannot create a crystal growth lab in Taiwan, because you people know I'm an Indian. Indian operate this much very big lab in a foreign country is very, very difficult. And also in my lab, mostly Indian students only. Thank you very much for all the audience, and really I like to thank Thangavel also give an opportunity to present my talk. Thank you, Thangavel.
Thank you very much. The wonderful talk for Dr. Sankar from Academy Seneca, and as well as the Crystal Growth Center also. It's a part of the parent institute. Now the talk is open for discussion. Faculty members and students are available.
Very wonderful presentation, Doctor.
Oh, thank you, Saravana. Thank you.
Yeah.
Yes.
And very impressive that I saw your publications from Nature and Science. And it is only very few publications you shown, I think, right?
Yeah. Very few only, because if you show too much,
we have
then
more
people
than
think
500 publications.
Yeah.
More than 500
mostly it's high impact papers you have. So I saw one slide about the Dirac crystal or something. you shown in the first few slides. Dirac,
and
in
Dirac
the first
semi-metal.
few.
Dirac
What
semi-metal.
is that? I don't know. What I can't understand that.
No,
Dirac semi-metal.
because Dirac mostly, if you talk about the topological insulator, mean the bulk metal is a insulator. The surface only is like a conductive nature. Okay, but in the Dirac semi-metal, you have a either hole pair or electron pair. You can see that in your semiconductor physics book, you can see the valence band or conduction band, right?
Yes.
Here we have a Fermi level. According to the Fermi level, how the band gap, the spin align in which direction? That's respect to we can, because it's a deep physics. I cannot explain because if you want, maybe I send that paper. You can read it because within a minute I cannot explain how the spin with spin orbital coupling or without spin orbital.
It happens only in the surface.
Yeah,
on
the
surface.
symmetry break, the symmetric broken only is happen when your metal have a symmetry broken is happen. Then the degeneracies have appear. Then we can clearly see that kind of phenomena. This is kind of new physics phenomena actually.
Because why I have asked the Dirac, maybe the electron distribution, it connected with the Dirac. So is there any relation with that in the name for Dirac semi-metal?
Because this the phenomena founded by Dirac, the one of the kind of person name. Okay, that's why we called as a Dirac semi-metal. Okay.
Okay, thank you. So I can ask another participants to go for a question.
Yeah, if you have a more question, anything, just send an email to me, because in my first slide is there. If you want anything, or if you want to utilize my lab, just send an email or send to ask Tangavel to provide all the contact details.
Yes, I will give the contact.
Just send the email.
I
never say no to you people. Okay, always welcome to collaborate, and also please send your students. I will take care of them and we train them also. Okay. Okay. Thank you.
Any other questions, Bharani?
Good evening. Good evening, Shankar sir.
Yeah.
I think your helping tendency is not ending till now, right?
See, we are nature of the
helping. Yes. Shankar sir, always passive approach. Very good. Very nice.
We came from scratches, right? We came from scratches, right? I need to help the people where I came from. Okay.
Okay. Thank you so much. Now the students from government colleges also attending this seminar, sir. But they are beginners. They are beginners to the research as well as the crystal growth. They don't know anything. What's your suggestion to do their research work from the beginning, sir? Your suggestions, please.
So this kind of master student or MPhil students there, we offering for every year 3-month internship program. We provide including accommodation as well as salary for them. Almost Indian money we give 80 to 90,000. Okay. Please, who are interested, definitely they need to join the PhD. Please send the application to us. According to our institute, we can take more than 10. Other institute also recently, lot of Indians coming for an internship program. Once they come, how the lab working, then they have to apply the knowledge, how the students are working. If they in the research atmosphere, definitely they choose their career. That's why I inform you. Please send your student, not only India, many places. They learn the new technique, then implement to India. And also I humble request for all the faculty member, join like a team. Don't expect you need to publish individual paper. No. Join like a team, then design one work and contribute everyone. One paper you put your corresponding author, other paper, like a team. If you have a facility or some people have a facility, make it 5 facility, prepare the characterization and go for a publication. But here for high impact paper, nothing too big you need to do, but you need to tell the story, why you did the material, what is the important, what is the new thing is there. Like if you saw movie, right, how you informed your friend, how you elaborate the movie story to your friend, right? Same thing, you need to write the paper like a water flow. There is no struck. But try If you are doing any characterization, you must check 1 or 2 times reproducibility. Once reproducibility come, then you write a story. Definitely, we can go for a high impact paper.
Any other questions from
Thank
faculty
you, sir.
members?
Thank you.
And welcome. Dr. Sangar is available. You can give any questions. You have more expertise, more than 25 years experience in the field of crystal growth and material characterization, and as well as in our devices also.
Tangavel, I forgot to
Shankar,
inform you.
Dr.
And also,
Dr. Vimalan,
we have a,
Dr. Vimalan, your friend is there.
okay.
He's now colleague. Vimalan.
Oh, okay, Vimalan, okay. And also the Taiwan offering for a project. Okay, the National Taiwan and Indo-Taiwan project is also there. Many PA you can apply. Almost they give 75 lakhs also. Please try your expertise who are available in Taiwan. Just apply through that one. They can give a postdoc, including instrument money and chemical money also. You can apply for any faculty. You can apply for that program.
Yeah, definitely. I will send my student to Academic Seneca. Again, I will come to the Seneca.
Thank you.
No, I didn't get for a postdoc. We need to apply any proposal for particular lab. Or?
No, Saravanan. You can apply through that project you are submitting, right? They can provide postdoc salary as well as your consumable, travel, including instrument, and also they support for a PhD student, one PhD student salary also.
Okay, that
both side you need to take authority letter from your head of the department or your institute, then submit to through national NSTC program, most program. Then, for example, if you and me join together, both need to agreement one side, then we need to submit. But area of expertise very, very important. Okay. Because they have more than 10 areas they are providing. Yeah.
Okay.
Dr. Sankar, I will request one thing. We can make the joint PhD program from Seneca and IIT.
There is a program there, TAGPX program. Okay. If your student doing PhD there, they can come and join. I can become a co-guide. We provide the facility. We provide the salary for them also.
Okay, then we have now students are available. I will make for the
no problem. They must become a second year PhD student. Second year PhD. They must complete. They must complete the second year PhD actually.
Yeah, coursework completed. I can make for joint PhD program.
Okay. Thank you.
Sir,
any other questions from the faculty members, students?
Sir, I have one doubt from my side.
From the Manit Bhopal. So I can join for the PhD for second year.
Yeah. You need to apply THB program. Okay. Then talk to your boss. He need to give a letter, and we also give. Then committee decide. Oh, your expertise, our center work is almost same. Mean that definitely we provide salary as well as accommodation, everything for you.
Sir,
okay. Yes, sir.
Can I register for PhD under you, sir?
Yeah. You can choose me also. But if you choose me, you need to work hard work, and somewhat I'm strict also. I informed you.
No, sir. It's fine, sir. It's fine for me, sir.
But you need to work 9 to 5. No need to work for 24 hours. Okay, 9 to 5 is job is okay for me.
Sure, sir.
Okay.
I think there is no questions. Let us thank big thank to the Dr. Sangar from Academic Seneca and as well as Crystal.
Thank you. Thank you very much for everyone. Thank you very much for everyone.
Still 25 years is same things we are looking. Still young persons like Rajinikanth.
Thank you, Tangavel. Thank you.
Thank you very much. Thank you very much once again to big thank. Okay, now one more resource person from the Dr. Sankar student is from Rajesh, IIT Roorkee. Recently, he joined with assistant professor in the nanoscience and nanotechnology. Let us welcome to Dr. Rajesh. He will deliver the speech. Trying to make use of two-dimensional material and devices. Let us welcome to the Dr. Rajesh deliver his speech.
So my slide is visible?
Yeah, yes, visible.
Yeah. Okay.
Yes, sir, visible, sir.
Yeah, very good afternoon to everyone. First of all, I would like to thank Professor Thangavelu and Professor Shankar for giving this wonderful opportunity to me be in the part of FDB program. So I'm very happy to be here. I'm just going to show my ongoing research and what I have done so far. So I'm going to discuss about novel two-dimensional materials in optoelectronic devices. The schematic view of my overall research work. First, we identify a material. Then we grow a single crystal of the material using various growth techniques. This was previously explained by Dr. Shankar. Followed by we fabricate a device on thin layer of the materials with the help of lithography techniques. And finally, we study the electrical and optical properties of the material.
Sir, your screen is not visible, sir.
Not visible?
No, sir.
It's okay.
Yes, it's visible. It's
No,
visible.
sir, it's visible, sir.
Visible only.
It's visible, sir.
It is visible, sir. Okay. Yeah. So
Yes,
the final part.
Visible only. It's fine. You can go ahead, Rajesh.
Yeah, sure. Yeah. So the final part is that we study the electrical and optical properties of the material with the help of transistor and photoreductor devices. So here is the outline of my talk. First, I give you a short brief about what is two-dimensional materials and how we can grow as a single crystal and their exfoliation and device fabrications, followed by the application of graphene in the electronics and the optoelectronics. Particularly, I will focus on the transistors and the photodetectors. Then I will talk about van der Waals heterostructure by stacking various kind of two-dimensional materials on one another. Then the 2D perovskites, which recently evolved in the 2D family. And finally, I will talk about the quasi-nanoribbon MOS2. Then the future aspects based on these two-dimensional materials. What is two-dimensional material? I hope many of you are well aware about this material. I'm going to recall it once again here. It is a layered material which are weakly stacked together to form a bulk, like three-dimensional structure. As we can see in the single sheet, the atoms in the same plane have a strong interaction. They will have a covalent interaction. But between each sheets, there's a weak interaction. It's called like a van der Waals gap. So we can easily break this van der Waals gap by some external force. We can also assume in the other way that number of single playing cards were stacked together to form a bulk deck. From the deck, we can easily take out a single card. So likewise, from the bulk material, we can easily separate a single layer of materials. Graphene is the first two-dimensional material which was isolated from graphite. As all know, graphite, which we are using from our childhood until now through a pencil. But the two scientists viewed the graphite in a different perspective. They were able to exfoliate a single layer of graphite called graphene by simple scotch tape exfoliation process. It's like peeling a thin slice of carrot using a peeler. Here they peeled a single layer of graphite by scotch tape. For this groundbreaking achievement, Andrew Game and Novoselov was awarded Nobel Prize in Physics 2010. Since the discovery of graphene, there are tremendous development in the material science due to exacting electrical and mechanical properties. However, the application of graphene is limited in the optoelectronics because graphene does not have a band gap. If you see the band structure, the valence band and the conduction band will meet at a point, it's called direct point. So there is no gap. And also it absorbs a poor light. Almost like 2.3% of light will be absorbed by graphene. So the application of graphene is limited in the optoelectronics. So the people were started to think about other two-dimensional materials, but which should have a optimum band gap. And they have come across so many two-dimensional materials such like transition metal dichalcogenides, metal organic frameworks, mexines, oxides, metals, plaque phosphorus, and hexagonal boron nitrate, among which the TMD, transition metal dichalcogenide based two-dimensional metal, attracted researchers are much more popular because we can tune the band gap in the range of 1 to 2.5 electron volt, which is very optimum for the optoelectronic application, because this band gap will lies in the range of visible light. How we can tune this band gap? Because as I said, that a two-dimensional material will be like layered structure. So by giving some external force, we can easily separate into a single layer or few layer or multi-layer. So you can see here, in the case of MOS2, this picture shows one layer, it's a mono layer. In mono layer, the MOS2, it acts as a direct band gap nature. It has a band gap of 1.8 electron volt. But when you increase the thickness of the MOS2, this will convert from direct to indirect band gap. So in case of two layer, it behaves like a indirect. Of course, in 3-layer, 4-layer, in up to bulk, it will behave as a indirect. Only in mono layer, it acts as a direct band gap nature. So by this thickness of the layer, we can easily tune the optical property of any two-dimensional materials. So theoretically, there were more than 1,000 2D materials were predicted, among which more than 100 were already produced and people were already studied. Why these two-dimensional materials attracted more than quantum dots or single one-dimensional or bulk material? Because 2D materials offer a superior electron mobility, because graphene has the highest electron mobility, which is higher than the silicon, and it acts as a good electron transfer platform, and it has a higher photo response, also act as a good photocatalyst, and has a very large surface area. And also these 2D materials offers maximum flexibility and the transparency, which makes the application of 2D materials in the fabrication of highly flexible and transparent electronics, as well as optoelectronic devices, as well as the large surface area. It's favor for the high surface active kind of application. So the 2D materials attracted applications, particularly in the battery, transistors, sensors-based applications, OLED, memory, and other optoelectronic-based applications. Let's see how we can grow these 2D materials. There are two approaches we can do it. One is the top-down approach, another one is the bottom-up approach. In case of top-down approach, we can grow a bulk crystal. From the bulk crystal, we can exfoliate with the help of mechanical exfoliation or by liquid exfoliation. We can exfoliate into a single layer or a few layered or even into multi-layer. So in the case of top-down approach, we can grow by chemical vapor transport or by bridgement techniques. So by these two techniques, we can grow a bulk crystals. From this, few layer and a mono layer will be exfoliated. In the another approach called bottom-up approach. In this approach, we can use a chemical vapor deposition or by physical vapor deposition. Using these two techniques, we can directly grow this mono layer or few layered two-dimensional materials. Let's see one by one. So in the chemical vapor transport, what we do, we take a growing precursor in a quartz tube and place it at a high temperature furnace. So with this, we'll also keep a transporting agent. So this transporting agent will help to transport from one end to the another end of the tube. Suppose in case if you're taking a precursor of A and B, and we will mix with some transporting agents. So when at high temperature, these precursors start to vaporize. So this transporting agent will help to transport from one end to the another end of the quartz tube, where we maintain low temperature. So this vaporized precursor will start to deposit as a tiny bulk crystals. The advantage of this technique is that it's easy to operate and the crystals can be grown at low temperatures. But the drawback is that obtaining a very large size single crystal is very difficult in this technique. So in order to obtain a very large size single crystals, and also for the congruent growth, we use bridgement techniques. In the bridgement techniques, the growing condition will be in the vertical direction. In the CVT, the growing condition in the horizontal direction. So here, there is no presence of any transporting agent. We directly take the precursor and heat it at very high temperature. So in this high temperature, the precursor will completely melt, Once the precursor is melt completely, we lower down our quartz tube to the lower region of the temperature. Again, here we use a two furnace. In the upper, we have a high temperature. In the lower region, we have a lower temperature. Once the precursor completely melt, it become liquid, then we will lower down into a low temperature of the region. There crystals start to begin, and we can obtain a very large size single crystals. Once the crystal is obtained, how we can exfoliate into monolayer or few layer is called by Scotch tape exfoliation process. It's a simple technique process in which a small piece of the bulk two-dimensional, we can say it's a bulk material, of course, but it is a layered in nature. So we can keep a small piece on this simple Scotch tape, then straightly start to rub on either end and peel it. And you have to repeat this process like several times. If you can see clearly when you have doing rubbing and slicing, that one piece become two, then again you are doing this process and then two piece become four. So when you repeat this process, there will be a multi exfoliation of your nanosheets, and finally we transfer this exfoliated nanosheets on the tape into a silicon substrate, because we use the silicon substrate for the device fabrications. So you can clearly observe the exfoliated graphites on the silicon substrate, and the arrow shows the lightish blue is the monolayer of graphene. The thickness of monolayer graphene will be around 0.3 nanometer in thickness. And also we can see like a few layer and multi-layer thickness. Due to the color contrast in the microscope, we can easily visualize these monolayers and a few layers. But finally, with the help of atomic force microscopy, we can measure the thickness of our exfoliated samples. Also, the drawback of this Scotch tape exfoliation is that the size limitation. By these exfoliation techniques, we can able to only exfoliate a micrometer range of nanosheets or even a few layered nanosheets. So in order to overcome this issue, there is people proposed called gold exfoliation technique. So with the help of gold, they are able to exfoliate even a millimeter to centimeter size of exfoliation, because gold has a strong adhesion to the materials. So in here they used gold evaporation on the silicon substrate, and they used thermal release tape as well as polymer. So they together with they exfoliate a sample, and once they transfer onto the silicon substrate, and they remove this tape with the help of because it's a thermal release tape. So at 130 degree, by heating, this thermal release tape will be released. Then they remove this polymer with the help of water. Then finally, the gold etchants, gold will be removed. So we are getting complete high size of exfoliated samples in the range of millimeter to centimeter size. The right side image, you can clearly observe the exfoliated samples are in the range of almost 1 centimeter in size. The another approach of exfoliation is called a liquid exfoliation. In the liquid exfoliation, on the 2D, the bulk nanosheets material will be placed in a probe sonicator, and by giving high frequency, these nanosheets can be easily removed under high frequency, and by final centrifugation, we can easily separate a nanosheets. In the another approach, we can also intercalate some chemical exfoliation by using a lithium ion insertion in between each nanosheets. So this lithium insertion will remove the nanosheets separately, and again by centrifugation, we can easily separate the nanosheets from the bulk material. Once we achieve our monolayer, few layer materials, then our next step is the device fabrications. There are several techniques that can be a device can be fabricated. So the most common technique we use like shadow mask fabrication. In the shadow mask fabrication, we use a TEM grid as a mask. So this is our exfoliated sample on which we placed that this is a TM grid which attached on a substrate. on a holder with the help of glue. Then we place this TM grid on the surface of our exfoliated sample with the help of a micro manipulator. Then we take into the thermal evaporator to deposit a thin film, I mean metal electrode. So in the image you can clearly see we placed TM grid on the top of our exfoliated samples. Then we deposit metal. Here we used gold metal to deposit in the empty space. So clearly you can see in the empty space we have a metal. Here in between these two metals there is our exfoliated sample. Now this channel act as a transistor. So between source drain we will have some semiconductor material that can be used for a transistor or photodetector applications. By this technique we can able to only fabricate a device like more than 20 micrometer size of materials. So in order to fabricate a device less than 20 micrometer or even in nanometer size device fabrication, then we need to go so high sophisticated instruments like such as photolithography and e-beam lithography. In the photolithography, like first we again we exfoliate a sample on the silicon substrate. Then we use photoresist on the top surface. We coat a photoresist. So in order to coat the photoresist, first we have to coat hexamethyl disilane, which help for the photoresist the strong interaction with the our material as well as substrate. Once we coat the photoresist with the help of coater, then we expose. Here we expose using ultraviolet light around 375 nanometer light. We expose the desired pattern. So here we want to fabricate this kind of structure. So we will have mask above on our material. Then we expose under UV light. So during this expose, what will happen? This photoresist will interact with the light. So in the space of the photo mask, there will be space, so it will interact with the photoresist. So there will be a breakage in the photoresist. So during the develop, the exposed part of photoresist will be completely removed. Then the unexposed part of photoresist will be remain same. Then we take into the e-beam evaporator to deposit metal film all over the surface. Then by lift off process, we will remove the unnecessary part of photoresist, and finally we will achieve a device which we need structure on the surface of our exfoliated MOS2. Similarly, for the nanometer size fabrication of device, we use e-beam lithography techniques. In the e-beam lithography techniques, we can pattern various kind of like structures, like multi electrodes easily we can fabricate. Again, it's similar like photolithography process, but here instead of photo, here we use a electron beam to directly we can write the structure. So in this case, we fabricate on a monolayer MOS2 with different type of structures. These are metal pads which can be helpful for the to study the electrical and optoelectronic properties of this single layer MOS2. So what are the application of these 2D materials in the optoelectronics and the electronics? So these 2D materials can be used in the transistors, photodetectors, photovoltaic device, and light emitting devices too. So what is transistor? As many of you will hear about transistor, which we know that transistor is everywhere in the mobile and telephone and also our computers. So what is a transistor? It is a device. It's composed of semiconductor materials which usually have a 3-terminal called source, drain, and gate. Between source and drain, there will be some semiconducting channel. So when we give voltage on this source drain, there will be a flow of charge carriers from one end to the another end. By the help of gate, we can control how many charge carriers can be flow from one end to the another end. So we can say it's kind of switch. So we can decide like how many charge, like if suppose if you want to send only 10 charge carriers mean we can control by with the help of gate. That's why we call it a gate. It's a electrode which control the charge carriers in between the source and drain. In the same transistor, when we shine light, what will happen? There will be excitation of electrons. So these excited electrons will be captured by the source drain electrodes. So we can say a photo detector is a photo transistor. So it's a device that convert light into the energy. So it works in the basic of the principle of photoelectric effect. In the what is the photoelectric effect? When any electromagnetic radiation will hit on a metal surface, there will be a ejection of electrons. So similarly, when we pass light on any semiconducting material, there will be excitation of electrons. So this excited electrons will be collected by surrounding source drain electrode. How we can calculate the efficiency, like how much current we are getting by light. So we called responsivity, photo responsivity. So number of photocurrent obtained per incident power into the illuminated area. By this relation, we can calculate the how much current we are able to obtain once light is fall on our device. So in this work, for the first time, we demonstrated a few layered indium selenide can act as a high performance photo detector. So we grown indium selenide with the help of a Bridgman technique, very large size, almost like more than 2 centimeter size of crystal we obtained by this Bridgman technique, and exfoliated with the help of a Scotch tape exfoliation, and demonstrated few layered indium selenide can act as a high performance photo detector. This is our grown indium selenide, and by with the help of Scotch tape exfoliation, we fabricated various thickness of indium selenide, and we demonstrated the single crystallinity nature with the help of XRD and SAD pattern, which confirm our the single crystalline nature of our growth material. Then we fabricated with the help of shadow mask technique, we fabricated a photo transistor device. Then we shine light on our material. So here we try to understand the nature of the material, whether it's a N-type or P-type nature. So for that, we try to give the gate voltage from negative to positive. So in the positive gate voltage, we can clearly observe very high current. In case of negative gate voltage, there's less current, which indicate that this material belong to a N-type nature. Because in N-type nature, when you give positive, the current will be high. In case of P-type nature, the current will be high in the negative region. Then we try to shine light on our transistor and try to extract the photoresponsivity. So as we can clearly see that when we increasing from minus negative to positive, we can clearly observe the increasing in the photocurrent as well as the responsivity. So when we calculate the responsivity is very good, high in number. And also we shown the flexibility. So we fabricated again we fabricated a device on the flexible substrate. In the previous case, here we use a rigid substrate, a silicon substrate. So we cannot use for a flexible kind of applications. So in order to use for the flexible kind of applications, then we use a different substrate called PET. It's a polymer based substrate, polyethylene tetrathlate. So this we can flexible. So the flexible application is very important for the real-time based users. So here we also demonstrated indium selenide can act as a high responsivity for the flexible based applications. Even in a bend state as well as a planar state, we are able to obtain a very good responsivity on our material. Followed by this indium selenide, in the another work, we try to demonstrate the intrinsic electron mobility of indium selenide is having very high as compare other two-dimensional materials. Other than the graphene, the 2D materials shows a very poor mobility. So in order to enhance the intrinsic electron mobility of a material, we come across a idea called coating the silicon substrate with various kind of material. So again, as I said previously that we fabricate a device with the help of exfoliation and shadow mask technique. We fabricated devices. So here we used 4 kind of substrate. One is called bare silicon substrate. In the another substrate, we coated a polymer called polymethyl methylate acrylate. Then we coat hexamethyl disilane on the another substrate, and we use the silicon nitride substrate. So in these 4 different substrate, we try to extract the intrinsic electron mobility of our pure indium selenide, in which we clearly observe the polymer coated silicon substrate showing a very high intrinsic electron mobility as compare other 3 substrates. Is because in between the substrate and material there will be some interfacial phases. So in the interfacial places there will be a lot of scattering effects will be happening during the charge carriers movement. So with the help of coating a few nanometer, a few micrometer size coating, it will help to improve this scattering effect. It will reduce the scattering effect. So by this way, we are able to improve the performance of the intrinsic electron mobility of a material. And also we grown a p-type based material called germanium sulfide. So here we can clearly see when we increasing the negative gate voltage, we can clearly observe increasing in the current, which shows this material belongs to a p-type nature. Then we shown it has a high on-off ratio, almost 10 power 5, which is quite good in the 2D family. And again, we shined a light on our germanium sulfide and try to extract the photo responsivity of our material. So we extract almost double the of indium selenide, and also we improve this responsivity with the help of gate voltage. As I said that previously, we can tune the number of charge carriers between the source and drain with the help of a gate. So when we increasing the negative gate voltage, we can clearly observe increasing in the responsivity. It's because of p-type nature. So we are getting high responsivity in the negative terminal. And also we try to demonstrate a broadband absorbance of our material. So we perform a photodetector from visible region from 400 to 800 nanometer. We performed this germanium sulfide can act as a broadband photodetector. And we showed real-time application by shining light on and off for the large time of interval. So we can clearly observe there's no degradation in the on-off cycle during during light on and off. It clearly indicate our germanium sulfide is a stable candidate in the ambient condition. And also when we varying the gate voltage negatively as well as source drain voltage, we can clearly observe the enhancement and decrease in the photocurrent, which shows the durability of our germanium sulfide photodetector. So basically, we can conclude that this germanium sulfide can act as a stable as well as a durable photodetector for the real-time based applications. Then we also focused on this light emitting divide. So in the light emitting divide, what is the principle of the light emitting diode is that when we give voltage on this source drain, there will be a injection of electron and a hole pair into our material. So this electron hole pair recombination will create a electroluminescence. This is the basic principles of the light emitting diode. So what we used in the studies, so we used various kind of electrodes on the surface of our material. So first case we used a palladium. We coated. We acted as a source and drain. In the device 2, we used a silver on the both end of the material. In the third approach, one end is a palladium and the another end is silver. So you can clearly see the optical image, the color difference between the silver and palladium. So by this case, we are able to inject one side, we can able to inject electron, and the other side, we are able to inject a hole. So in the case of, you can clearly observe, we are able to get both p-type as well as n-type due to the palladium and the silver. So we clearly observe ampipolar nature by the help of palladium and silver. So by having this electron and hole injection, there will be recombination is happening in the indium selenide. This recombination will create a electroluminescence, and we observe a wavelength around 1000 nanometer, which clearly conforms with the band gap of indium selenide, which belongs to around 1000 nanometer. So by this way, we are able to achieve indium selenide can act as also a good LED based application with the help of various kind of combination of electrodes. Apart from the binary based material, we also focusing on ternary based materials in order to enhance the performance of device, as well as to expand the broadband applicability of your photodetector. So in this case, we grow a tin sulfoselenide like SNSSE, and we exfoliated a very small nanometer, almost 6 nanometer thickness of material, and demonstrated a device photodetector on this, and shown a very high photoresponsivity, which is quite higher than the previous case of like indium selenide and germanium sulfide. And another work, we grown hafnium sulfoselenide nanosheets by CVT technique and demonstrated its high single crystalline nature with help of XRD as well as with the SAD pattern, and demonstrated this hafnium sulfoselenide has a broadband detectivity. If you see only hafnium diselenide, we will have a pure absorbance in the visible region. In case of hafnium diselenide, it has absorbance in the region of near infrared. So by having 1:1 of hafnium sulfoselenide, we are able to expand the absorbance from visible to near infrared. So by this way, we are able to prove that hafnium sulfoselenide can be act as a both visible photodetector as well as infrared photodetector. In case of visible photodetector, we shine around 488 nanometer wavelength and able to extract a very high photoresponsivity. In case of near infrared, we shine 980 nanometer laser under a flexible device. We also achieve a very good responsivity. So we proved hafnium sulfoselenide can act as both visible and near infrared photodetectors. Recently, I am also focusing on a van der Waals heterostructures by stacking various two-dimensional materials on one another. Why we want to stack various kind of two-dimensional materials? Because in order to create a PN junction device, we need like one kind of P-type material, and we need a N-type of material. So we can stack various kind of two-dimensional materials, and we can fabricate a device. If you see the like structure, it's look like a shape of hamburger. You can consider like a hamburger. On the top and bottom, we will have a metal electrode, and in between the hamburger, we will have a lot of stuffs, right? So we can like this like kind of stuffs, we can place various kind of two-dimensional material on one another. So by this way, we are able to achieve like a PN junction device, and we can enhance the performance of the device, and of course the broadband applicability of the device. How we can do? Again, this can be possible with the help of exfoliation techniques, with the help of micro manipulator. So in the first case, similar like the exfoliation technique, we have to exfoliate a first material on the silicon substrate. The second material which is going to stack on the first material, we have to use a PDM as a polymer substrate. So we have to exfoliate on the surface of the polymer substrate. Then we have to stamp on the first exfoliated sample with the help of microscope and a manipulator. With the help of manipulator, we can stack the various two-dimensional materials on one another. So you can clearly see here we exfoliated here the exfoliated boron nitrate. On the top, we can exfoliate graphene. Again on the top, we can exfoliate one more boron nitrate. So if you see here, there is a three two-dimensional materials like boron nitrate, graphene, then again boron nitrate. So likewise, we can stack multi-dimensional 2D materials on one another. So by stacking this kind of materials, as I said, we can able to improve the performance of a device. So in this study, we stacked germanium, indium selenide and germanium sulfide. So here indium selenide is a N type and germanium sulfide is a P type. So here we create a PN junction device, and we try to study the photo responsivity and observe a very high responsivity, which is quite higher than the binary based indium selenide and germanium sulfide. On this work, we exfoliated indium selenide and tungsten diselenide, and also we placed hexagonal boron nitrate, and we fabricated a device. And interestingly, we observed anti-ambipolar behavior. So, what is ambipolar behavior? Ambipolar behavior, I shown previously, it has both P type and N type nature. So, it will be like a V kind of structure. But in the studies, we observe a inversion of V. It's called anti-ambipolar. So by this creating this kind of structure, we are able to achieve this anti-ambipolar behavior on the structures. Also in the another work, we quote quantum dots on the surface of indium selenide. We prepare quantum dots with the help of simple solution process, and deposit these quantum dots on the surface of exfoliated indium selenide and try to extract the device performance. And we observe in bare silicon substrate the responsivity in the order of 100. In the presence of quantum dots, it's improved twice the order, two order of magnitude higher than the bare indium selenide. And also we demonstrated this structure, the combination of MOA, quantum dot MOS2 and indium selenide can be used for solar cell kind of applications, and we are able to achieve around a 3% efficiency. And very recently, I'm also focusing on the 2D perovskites. In the previous talk, Professor Shankar was talking about this 2D perovskites. Yeah, again, as many of you know about the perovskite, the importance of the perovskites, it plays a major role in the recent solar cell application, because perovskite has a very large absorbance spectrums. That band can be tunable, and it gives a very high power efficiency, and it's a very cheap material. So people were started to use these perovskite based materials. So if you see the general structure of the perovskite is the ABX3 structure. So here A is a cation and B is a metal ion and X is a halide ion. The drawback of this bulk, this is a three-dimensional based perovskite. So the drawback of this three-dimensional based perovskite is the stability issue. When we expose this perovskite to atmospheric conditions, or when we irradiate with light, and when we increasing the temperature, or even exposed to moisture, these materials easily decompose. So in order to improve the performance of this perovskites, the new family arrays called two-dimensional perovskites. It's nothing but in the three-dimensional perovskite, between each perovskite, there is a presence of one organic spacer. So this organic spacer help in improving the stability of a perovskite, because this is a hydrophobic nature, so it will easily oppose the water content. So this improve the performance of a material. So the another advantage of this 2D perovskite is this tunability. So we can tune the number of layers of each perovskite, similar like two-dimensional material. It is also a layered nature. So in case of n equal to 1, we'll have a single perovskite. So between two single perovskite, there will be a two organic spaces. In case of n equal to 2, there will be two perovskites. Between two perovskites, there will be two organic spaces. When n equal to 3, there will be three perovskite layers. So likewise, we can tune on the number of thickness of perovskites. So between each perovskites, there is a presence of organic spaces, which improve the stability of a material. So in this work, for the first time, we demonstrated For the first time, we grow a very large size single crystal using a solution growth technique. Almost we grown like 1 centimeter size of formamodium butylamine formamodium based lead iodide perovskite, and we shown as a very good high crystallinity in nature, and demonstrated it has a very strong stability as compared methyl ammonium based perovskites. So you can see in the optical image and the photoluminescence. In case of presence of formamodium, can clearly see in the optical image there is no degradation in the optical image as compared with methyl ammonium based. In the methyl ammonium based, almost 60-minute exposed to light, it's almost the like a lot of the layers is degraded. So the same phenomenon which we are observed in the photoluminescence. In case of 30 minutes, we like almost half photoluminescence come out. Then when reached to 1 hour, completely the photoluminescence is quenched. But in case of formamodium based perovskite, we are able to see a good stability, very small amount of degrees in the unit. Why this formamodium based is so higher response, higher stability as compare methyl ammonium is because this here the size plays a major role, because the size of this formamodium ion is a very large size. So this large size is able to strongly incorporate into the perovskite structure. So the movement of ions will be less as compare methyl ammonium, because the size is small. So the migration of ions is high in the case of this structure as compare FA based structure. So by this way, we are able to improve the performance of material. And we also demonstrate the same phenomena in the device part. As can clearly see, when we switch on the light and off, the on-off current is increasing constantly without any degradation. But while in case of methyl ammonium based application, we can clearly observe when it reaches to 20 minutes, it start to degrade, and almost in 1 hour, it's completely degraded, which prove our FA based material is a strong candidate for the optoelectronic based applications. And again, we shown this material can be used as a flexible photoreductor, and we obtain a very good high responsivity on our flexible device. In order to increase the performance of the perovskite further, then we remove this van der Waals gap. So in the previous case, we can say that perovskite is a Rudolphson-Popper perovskite. In this structure, there's a presence of van der Waals gap. So because of this van der Waals gap, we can exfoliate similar like two-dimensional materials. In this another approach, we remove this van der Waals gap, and we will have only single spacer which directly attached on the both end of the perovskites. So there is no presence of gap. So again, this removing of gap is further increasing the stability performance of your material. So in this paper they have reported, you can clearly see in case of presence of van der Waals gap, the stability is the efficiency is around 9%. While removing the van der Waals gap, they are able to increase the efficiency almost 14%. So in this study, again by solution growth, we grow a bromine-based 2D materials by using a different spacer and achieve good stability all over the part. You can see clearly see the photoluminescence mapping clearly shows that our growing perovskite has a photoluminescence everywhere. Then again, we showed photodetector performance, and we achieved a very high responsivity. And we also shown for the first time, this material can have a random lasing phenomena. We can clearly observe in the photoluminescence there are a lot of small spikes which indicate lasing phenomena is happening on our material. This is because our material has a like pyramid kind of structure. So this irregularity of the steps is help in the random to occur the random lasing phenomena. We also like studied like quasi-MOS nanoribbon by with the help of pulse laser deposition and by chemical vapor deposition. By using these two techniques, we are able to grow a quasi-nanoribbon structures. As you can see, like we obtain three kind of structures like a monolayer MOS2, then bulk MOS2, then quasi MOS2 nanoribbon. It's a combination of one-dimensional and two-dimensional. This is a bulk one-dimensional MOS2 surrounded by monolayer two-dimensional MOS2. So we can say is a quasi MOS2. So again, we fabricated a photodetector on these quasi structures and demonstrated a photo responsivity, and we achieved a very high responsivity as compared a monolayer MOS2. So this comparison table with the normal two-dimensional material and with our quasi MOS2 structure, and we obtain a very high responsivities. So what are the future scopes on these two-dimensional materials? As I said that if you have like a van der Waals structure, we can improve the performance of your devices. Already people try to look this 3D perovskites and 2D materials. But as I said that the issue of stability, which makes 2D perovskite is a strong candidate for the future-based applications. So by having this 2D perovskite and two-dimensional structures, we can it offers a unique platform to understand the charge transfer mechanisms and also the light matter interactions, and also it will helpful to improve the high performance of devices, particularly in the photodetector, solar cells, and light emitting based applications. So there are a lot of scopes which is still available to study the 2D perovskite and the two-dimensional material stacking. So finally, I would like to thank all of my supervisors. Without their support, I can't achieve these things. And again, I would like to thank the committee for giving this opportunity once again to me. Thank you for your attention.
Yeah, thank you very much, Dr. Rajesh from IIT Roorkee, and as well as from Academy Seneca Taiwan. I would like to thank both Dr. Sangar and Rajesh. Now the talk is open for discussion. The talk almost is excellent talk for the two-dimensional material and devices. We know that, but we are not working the direction for the field effect transistors. But this talk is useful for the exploration techniques in 2D materials then and material device and fabrications. Let us thank Dr. Rajesh. One more big thank to him.
Thank you, Professor.
Yes. Now talk is open for discussion. Faculty members and students, welcome to the questions. Is more relevant talk things. Is almost the device levels. Hello? I think everyone is available.
Yes, sir.
Yes. Just please ask questions. Then only the resource person will be encouraged. So much encouraged. I think you beyond the limit. The talk is more high level talk. I think you can understand now. Everybody know the field effect transistors, source, drain, and gates. Then how the active layer structure is coming and the substrate selections. Maybe I think you know that.
Yes, sir.
Yes. Any clarification also you can ask to him. That's not issue.
Yeah, not only question, anything related.
Clarification also you can ask. Not only the questions, you can ask the any clarifications like that. Okay, then I will start the questions. I have some clarification, Rajesh.
Yeah,
you are trying to make the flexible devices.
Yes.
Okay, while do the flexible devices, what happened the strain parameters, strain engineering, your calculator?
Strain actually, we
I
didn't go
I didn't see your presentation. Strain involving studies not available. In your presentation, I hope you done, but
we
in the
didn't go
presentation
that
not included.
we didn't go that deep, like mechanical flexibility of a material. It's just like only showing a just bending nature and planar nature. Only we use these two process. We didn't go like a different stress kind of studies. We didn't go, but it's a good point that we should think about in the future.
Yeah, I have done the theoretical simulations in two-dimensional material. One of my PhD students completed PhD recently in MOS2 structure. We have studied in the strain-induced parameter in the MOS2.
Okay, good.
That's why I asked the questions. In the exploration techniques, what is the minimum layer thickness we will get? You are trying to make the
we get a monolayer we can get.
Monolayer structure will get.
Yeah. That
we can go up to monolayer.
That's why I'm asking too.
The normal like Scotch tape is quite difficult, but if you try the gold exfoliation process that I showed, by this way we can able to achieve monolayer.
Monolayer structure we can achieve.
Yeah, you can try with that technique, gold exfoliation technique.
Yeah, chemical vapor deposition, this kind of triangle lattice come definitely. You can go for a monolayer.
Okay. Then we verify by Raman spectrum. You are verified. Okay. Then one more another question. I have you are talk about is ambipolar transistors.
Yes.
Okay. Then in ambipolar transistors, you are showing the characteristics peak in N type is fine, but P type is now you have some defect levels are present in the samples.
Yes.
But now you are not getting that much level in the negative regions.
Yes.
What is the reason? Can you explain?
Because we use N type indium selenide. The material is a N type material.
Indium selenide only you are using for ambipolar character. But in the positive region is fine. You are showing the characteristics, is showing the current flow from the source to drain. But in the negative region, the drain to source is coming, then electron leakage is coming.
Yeah. Because
what is the reason behind?
The reason is that here we are trying to inject through holes from like silver, so it's not that effective because naturally our material is a N-type material. So in this N-type material,
this naturally is N-type materials. While changing the gate voltage is going, the leakage current is more leakage is coming there. That's why I'm asking the questions about the electron blocking available there in the device levels.
Yes.
Maybe
it's happening. Sometimes the leakage, leakage will be sometime more. It's happening.
Yeah, that is the things only. Things my questions. And one more, you are writing the anti-ambipolar characteristics.
Yes.
What is that anti-ambipolar? I didn't heard the name today. Only I think anti-ambipolar.
Yeah, just same like
this is a very nice definition. I heard only ambipolar. I know that, but anti-ambipolar. Could you explain briefly what is that?
I just
as physics point of view.
Ambipolar. Reverse of ambipolar behavior.
Yes, reverse ambipolar. What is the physics involving there?
Physics involved in that it's like it's like going N-type, then suddenly it is coming P-type. That behavior is called like anti-ambipolar.
Okay.
At a short point, then it coming down. Okay. So that we achieve because of this irradiation we achieve because of laser irradiation.
Yes. That is the things only. I think any other questions? I think it's very nice explanations. Rajesh, Dr. Rajesh. I hope everybody is enjoy the talk. Any other questions from audience? Please welcome. Yes, please.
Hello. Hello, sir. Thank you, sir, for such a wonderful talk. I have just one doubt. I don't know whether it is okay or not. Like this 2D perovskite, is it similar to the layered perovskite, that is bismuth layered perovskite, or it is different?
Yeah, same. Yeah, same. That's why we call 2D perovskite. We can exfoliate.
No, can you ask your question
Like
again?
it is similar. So in a perovskite material, there is one family that is Aurelius family, bismuth layered ferroelectric structure family. So is it similar to that 2D 2D perovskite, or it is different?
All are same only. They use a bismuth on the because of lead. That's why they called bismuth based perovskite.
Okay, sir.
Okay.
So
because why they use bismuth mean lead is a toxic material. They want toxic free 2D perovskite. That's why they use for bismuth based 2D perovskite actually.
Okay, sir. Thank you so much, sir.
Rajesh, excellent talk, Rajesh. Really excellent talk.
Yes, the talk is more excellent talk. Some audience are asking the size of the transistor we can make in 2D. What is the question?
Size 2D. Yeah, that's
no, he
like,
has
yeah,
one start box is written one person. I think students maybe size of the what is size of the transistor like that is asking.
Transistor size.
Transistor size or material size?
I think no. He asking about the size of the transistor. For area of the substrate, he is asking. Area of the substrate, I think.
It's very big. It's in the centimeter.
Yeah, he asking the size of the substrate. He asking, and what is the channel width you are using? That maybe he is asking like that.
Channel width, it's vary from 1 micrometer to 20 micrometer. The channel.
Okay. Then Harishta, one question: how will we extract field effect mobility? Like that one question. How will we extract the field effect mobility?
By performing this IV measurement
characteristic,
curve. So we have to apply in the form. There's a formula to extract the field effect mobility. So we call like as a transfer curve. When we do IVG measurement, then we can get the transfer curve. From this we can extract.
Yes.
Suppose
we
like this one, by this one, here. We can show the good one.
Yeah, you can
so
show the
by this
thing.
This is called a transfer curve. So when we measuring from -80 to 80, we know the how much current is we are able to get. So that's a formula for the to extract the field effect mobility by putting this all the values like what is the voltage we applied, what is the current we got, what is the length of the channel, what is the width of the material. So when we put all the data, then we can extract the mobility of that material or device.
Sir, one more thing. Then the people are asking is for the defect level in the when you are using the 2D semiconductor. What is the defect? For example, indium selenide or gallium sulfide. What kind of see? This is all are while do the explanation techniques. What will happen? The oxygen contamination may occur. They degrade the layers. Whether you are while do the fabrication, whether you are trying to make the any encapsulation you are using, that kind of all in
no,
condition
we are not using any encapsulation. Depends, but not in most of the cases we are not using. But
because
there will be some deficiency, like in case of selenium, sulfur, always there will be some deficiency. We can go like exact like 1:1. There will be some
for
deficiency.
indium selenide, very stable one. There is no oxygen contamination.
Contamination may occur in the indium selenide.
But in this case, I think we never face this kind of problem. Indium selenide case,
that is fine. Any other questions from faculty members? I think it's very excellent talk. People, I think everybody is available. I think Nandu is showing video.
Rajesh is
available,
a device expert.
Barani, all.
Yes, available, Tangavel. We are available.
Yes, you can ask questions. People keep silent, then
very
it's not good for us.
Explained. Very nicely explained. We are available.
Actually, Raj is expert in the device point of view.
But clarifications, whether everything completely understood or not understood, that is the things.
Completely
the two kind of things will happen.
And also Raj is
Completely
also looking
understood.
for PhD student. Tangavel.
Yeah,
This
yeah.
student
No,
apply for Raj's also, okay?
Yeah, recently I joined,
No,
so I'm
I'm
looking
not
for
understanding. What is that?
Raj is also looking
no.
for PhD student.
No.
Because he's
Rajesh
expert
is
for
now
device,
faculty members.
everything. If anybody
Yeah,
want
student,
interest for making device, just to follow Rajesh also.
Yes. That's why I see Rajesh done so excellent work. We are trying, but we are not achieved that part. That's why I talked to the first I talked to you, then you suggested Rajesh you include the FDP talk, then it's good for the audience. Then FDP
Yeah,
is
we
not
don't have
fulfilling.
facilities. We don't have facilities. There is a problem. Otherwise, we can do here also, but no
IIT
facilities.
Roorkee, no, IIT Roorkee have a lot of facilities.
No. Here related to device, I didn't found anything. I mean, like lithography technique.
They center research facilities are also available IIT Roorkee.
Yeah, but
They
for
have,
lithography, they don't have.
You need
for
a clean
the device
room.
part.
Tangavel.
Clean room
You
facility,
need
they
a
don't have.
high clean room you need.
that
Like it's
is clean
Academia
room. That is
Sinica.
Taiwan. Sinica have clean rooms. That's why you have done a lot of work there in the Sinica clean rooms. I think any other question I will check here. I think almost is done. I would like to big thank to the Rajesh and Dr. Rajesh and Dr. Shankar for excellent talk. Both are given the excellent crystal growth techniques and as well as the device material, two-dimensional material fabrication devices also. It's almost I will big thank to both of them. Everything.
Okay,
Thank you,
thank you.
Tangavel.
Thank you,
Thank you for
Professor.
nice opportunity for us.
Yes, Sangha sir, you can share the PPT and the audience I can share. Both are you can give the PPT.
Definitely.
Then I can share the audience. Then they will get benefit from the your talk, and as well as they will try to make collaborate with you. I hope everybody they will take this opportunity, collaborate with Dr. Sangar and Dr. Rajesh. Both are in now academic field things. Opportunities are available, upcoming things. Maybe now I hope Dr. Sangar is working in that quantum material device. I have one clarifications things. Can I ask one question?
Yeah, no problem. Go ahead.
Okay, now we are everybody facing the problem is quantum material devices things. Then classical computers they're trying to make quantum devices. What is your opinion? That is my questions.
No, recently we prepared a quantum qubit. Actually, 2 qubit.
Qubit. That is my question. Qubit only.
Yeah, we make already using a high temperature superconductor as well as NBSE2, NDM arsenic. We demonstrate 2 qubit. Okay, I think Taiwan now leading for a qubit one. We create a separate center for that one. If you people interest, then we can join together and work for this also.
I'm working. See,
That's
I
why
already started the course in the qubits.
That's why we working for a layer superconductor, Tangavel. That's why we working for layer superconducting material.
Okay. Thank you.
Thank you
is kind of excellent talk, Dr. Sangar and Dr. Rajesh.